This video is the second video in a three-part video series discussing the basics of polar curves and polar coordinate systems. This video is designed for a Calculus 2 course. It is based on the OpenStax Calculus book, Volume 2, Section 7.3, which deals with polar coordinate systems. In this video, we're going to narrow our focus and just look at identifying the polar curve by transforming from a polar equation to a rectangular equation. And also, we'll take a look at symmetry. I will also use a TI graphing calculator as well as Desmos to show you how to use these to do polar graphing. Let's start with example 1. In example 1, we are asked to identify the polar curve by transforming a polar equation into rectangular equation form. This is a very simple equation in polar form. Let's see what it looks like in rectangular form. Remember that in order to convert from polar equation form to rectangular or vice versa, we have some basic relationships. Here are the relationships we have so far. We know, for example, that x squared plus y squared will give us r squared. This is from the Pythagorean theorem, but is also true because, of course, the polar axes are based on circles, and we can think of it in this way. We also know that we have a relationship between x, r, and theta, that x is equal to r times the cosine of theta. Remember that this equation is coming from the cosine of theta being defined as the adjacent side over the hypotenuse on a unit circle. Our circles are no longer necessarily radius 1, so we have to use r for the denominator. We also have a relationship between y, r, and theta, that y is r times the sine of theta. And again, this relationship is coming from the definition of sine of theta as the ratio of the opposite side, y, to the hypotenuse, in this case r. Those three equations give us our basic relationships. We do, however, have a fourth relationship which we will occasionally need, especially when we're looking for slope. This is the one that says the tangent of theta is equal to the y-coordinate divided by the x-coordinate. Let's look back at the equation that we have here. We have that r is always 2. All we're given is something about r. There's no theta present in this polar equation. So it doesn't make sense to use either the x equal equation, the y equal equation, or the tangent of theta equation. All three of those involve the variable theta, which we do not have in this polar equation. That directs our focus to the only one we have left, which is x squared plus y squared equals r squared. Now we'll go ahead and rewrite this equation. If we rewrite the equation using that and substituting in place of r the value of 2, we get x squared plus y squared equals 2 squared, which of course is just the equation for a circle which is centered at the origin and has radius of 2. That is, in fact, what this one is. Let's take a look at how to produce the graph on a polar graph using a TI calculator or using Desmos. The one that you can see now in the window is a TI 84 Plus Silver Edition. It's at least 10 years old. No, you don't need the latest and greatest in order to do what you need to do. Yes, the TI Inspire would be my calculator of choice, but they are, of course, extremely expensive. And at this point, the basic will do. If you're looking at this, the first thing you do, of course, is to turn it on. Once it is on, let's go to the mode button. The mode button can be found here at the top. Press mode. Notice that you have it currently in function mode indicated by the fourth line down. If we move this down to the fourth line, I need to move it over to polar mode. That's the third choice that I have here. Moving over to polar mode, I will end up putting it on top of there and then hitting the enter button to turn it dark. This will put it into polar mode. To tell that it's in polar mode, now move up to the top and press the Y equals button. When you press the Y equals button, you will get the polar mode screen. Notice that instead of the parametric mode, which gave you a pair of equations for both x and y in terms of the parameter t, in polar mode, we get a possibility of different equations, but all written in terms of r. You'll see I already have one in here. Let's take a moment and enter the equation that we had before we began looking at the calculator. To clear out what's in there now, I simply need to hit the clear button, which is below the cursor keys, which move it up, down, left, and right. Our equation was the simple equation that r equals 2. Move down to the bottom and enter r equals 2. This will give us a polar graph. Now, in order to change things, we'll have to learn how to manipulate the window. I do want to warn you that this is probably the key to using the graphing calculator well. Let's click on Window now, which is down here. Notice in the screen that you have a theta minimum, theta max, theta step, x min, x max, x scale, y min, y max, y scale. You have a lot of choices. However, you really only need to set the first 3. Use the graphing calculator's technology and abilities to help you produce the best graph possible. That means don't work harder than you have to. We do want to set the theta values since theta is the independent variable for on a polar coordinate system. In this case, remember that the button that you see here, which gives us the variable depending on the mode. X in function mode, T for parametric mode, theta for polar mode, and N for sequential mode. We're in polar, so our variable will be theta. A typical window would include 0 to 2 pi. Remember that pi is often found above the caret key, which you can see here in a dark blue color. You'll notice that my window is already set to go from 0 to 2 pi. Below that is theta step. I am going to tell you why you need to choose a good theta step by demonstrating what happens when you choose a bad one. We'll start with the good one, which is the one I have here. Now, what do I mean by let the calculator do some of the thinking for you? I know what I want theta to be. I want theta to go from 0 to 2 pi. However, I want to let the calculator decide what the best window for the x-coordinate and y-coordinate should be in order to see the graph reflected well. To do that, I'm going to choose one of the zoom options. The choice I'll make will be zoom fit. Zoom is usually the center button below the screen. If you click zoom, you can either scroll down using the down key, or you can enter 0 to choose zoom fit. Zoom fit is probably my very favorite button on the entire zoom menu option. Zoom fit is going to say, okay, for theta values between 0 and 2 pi, the calculator will pick the best x and y screen values. It will pick the best x minimum, x maximum, and x scale. The best y minimum, y maximum, and y scale. That means I only have to set theta and theta step. Hit enter to choose zoom fit or 0. You'll notice that the bars are moving as it's working. Now this is my circle, which while it is curved, does not look remotely like a circle. What's the problem? The problem is Texas Instruments made their graphing calculators for decades with a rectangle screen. This screen is rectangular in shape. It's not square, which means that the distance on the x-axis and y-axis are not the same. First, you'll choose Zoom Fit to get the best x and y window. Then you'll choose Zoom Square to make the distance on the two axes the same. This will give the picture in the right proportions. Hit zoom again in the center and select option 5 or scroll down to choose zoom square. Now you can see that I do in fact have a circle, a perfect circle if you will. Let me point out some other features about the TI graphing calculators that is not an option on Desmos at this point in time. This makes the TI graphing calculator a better choice for polar graphs than Desmos. That choice can be found up here on the Y equals button. Hit Y equals to return to that menu. You'll notice to the far left that there looks like a dotted line of 3 dotted lines coming down. Move your cursor until it's on top of the 3 dotted lines and they begin to blink. Once they're blinking, move to the Enter button and hit Enter twice in order to get what I call a key. This reminds me of an old-fashioned skeleton key. What this does is the hyphen actually represents the line for the circle that's going to be drawn. The 0 that follows the hyphen represents a point. In other words, it's going to show you how it is graphing, where it starts, where it stops, and which direction it goes as theta changes from 0 to 2 pi. After selecting that, come back up to the top and hit the Graph button. Now don't take your eyes off the screen or you'll miss it. Do you see that it started on the positive x-axis, is tracing counterclockwise, coming around now to theta equals pi, now down around to theta equals pi over 2, and coming back around to theta equals 2 pi where it stops. Using this on the graphing calculator can let you discover where different values are on your polar graph. Unfortunately, in Desmos, we don't have this option. Let's look and see what's so different about Desmos and why, in some ways, the graphing calculator is better. You can see before you now what it looks like in Desmos when you come to a regular graphing window. This, of course, is a square graph, which is not going to help us since we're now in polar coordinates. We need to click on the gear, which looks like a wrench, and we'll tell it to graph in polar coordinate system by clicking on what looks like a target here. That takes the other square grid off. I've not found a way to keep them both on at the same time, though I think that would be a great option. For now, we'll simply click on this, which does give us our polar graph. Once we're in polar mode, then Desmos will expect R to be the variable. Unfortunately, the way that Desmos is currently programmed, you can only use R to a first power, which means if your equation has R squared, that you will have to write it in 2 pieces, one with the positive root and one with the negative root. Our equation, however, is quite simple. Ours is just R equal 2. If you enter R equal 2, did you notice what happened as soon as I stopped typing the 2? It immediately produced the picture, but it did not trace it. And this is a big disadvantage to using Desmos for polar coordinate systems. There's no way to force it to go slowly and to let theta change from 0 to 2 pi. It graphs the graph in one fell swoop, and we cannot see where it starts or stops. This is a big problem when we get to area and to arc length, as you'll see later in the next videos. This, however, is a good way to produce graphs to be sure that it looks right when you produce it on your graphing calculator. Desmos is fast and it is accurate and it does produce better looking graphs, but it cannot give us the information about where the graph is at a particular theta value. And that is something we will need when we compute area and arc length. Let's move on to the next part. In example 2, we're asked to identify the polar curve by transforming from the polar equation into a rectangular equation. This time we're told that r equals 3 times cosine theta. Let's write down again what our 4 equations are that convert from one form to the other. We have x equals r cosine of theta, y equals r sine of theta. These, of course, come from the definitions of sine and cosine on a circle. Then we have the Pythagorean theorem, x squared plus y squared equals r squared, since this, of course, means that sine squared plus cosine squared will give you the radius squared. Then we have the tangent equation, which can give us the slope of a point. This is the y over x, the ratio of y to x. Looking again at our polar equation, which we have up here now boxed in purple, I have r equals 3 cosine theta. I gotta tell you, it's looking a little bit like the first equation that I see here because of the cosine of theta. In order to get it in the right form, what I could do is since this is r equal 3 cosine theta, I could solve for cosine theta out of each one and set the two parts equal. Let's see what that would lead to. From this equation here, I have that x divided by r must equal cosine theta. From the equation up here in purple, I would get r divided by 3 equal to cosine of theta. However, these have to be the same cosine of theta, which together, this then implies that they must be the same, that x divided by r has to equal r divided by 3. Now, what can we write instead? If we have x over r equals r over 3, what might our next step involve? In my next step, if I look at this proportion, which of course is one ratio equal to another ratio, I can solve by cross multiplying the 3x and the 2r's, which of course would then lead to the following equation, that r squared is equal to 3x. But I have a relationship up here between r squared and x squared and y squared. Again, that this would then imply that x squared plus y squared must be equal to 3x. This is in fact an equation in rectangular form. This is in fact an equation for a circle. If you wanted to look at it a little bit more in depth and see where the center was, you would have to complete the square. I'll do it briefly for you. Pause the video, see if you can do it yourself, turn it back on, and let's see how we did. How'd you do? Yes, I know, this is a blast from the past, way back in college algebra or pre-calculus. In order to complete the square, you need to move the term 3x to the left to join the x squared. Once you do that, you isolate the two by just creating some space between them and the y squared term. Find b divided by a to determine whether or not you need to factor something off of the x squared. Of course we don't, since the coefficient of x squared is 1, and we get that b over a is -3, which is, of course, the coefficient of the x term. We isolate these two in parentheses. We compute half of that previous value, which is -3/2. When factored, that is the number that will appear in the binomial that is being squared. Then we square that number to get 9 over 4. This is the number that we must add and subtract, in other words, add 0, so that the first three terms with the positive 9 over 4 becomes the binomial squared. However, the minus 9 over 4 is still there and must be taken into account. We bounce it out by multiplying it by whatever the coefficient of the entire parentheses was. In our case, nothing, but actually that's something. It's a 1. 1 times the -9 over 4 makes it negative on the left, but if we move it to the right, it becomes positive 9 over 4. You'll see at the bottom in black the form for the circle. The center is at -3/2, 0. The radius is the square root of the constant on the right, or 3/2. You can tell now by looking at this that this is in fact a more complicated relationship. It's a more difficult formula. Let's look back up and see what the polar equation looked like. Yeah, just 3 cosine of theta. Let's now produce this graph on the graphing calculator and on Desmos so that we can see what the relationship is. We know what the relationship is in rectangular coordinates. Again, we know that the center is at positive 3/2, 0, which means that the center is on the positive x-axis. Let's put it into Desmos and the graphing calculator and see if that's what we get. Using Desmos first, we can see that we have r equals. Notice that we are in the polar mode because we have a circular graph to the right. Then we simply enter 3 cosine of theta. Now you can either use the drop-down menu or drop-up menu down here at the bottom by clicking on functions and going around the miscellaneous to find the theta. However, I will tell you it is faster to simply type theta, T-H-E-T-A. Once you hit the last A, it will convert it into the Greek letter theta. You'll also notice that it immediately popped up without giving us any chance to see how it actually traced it out. But you can tell that it is moved to the right. You're going to want to remember this later in this video when we'll talk about the relationship between a cosine and the fact that the circle is been moved horizontally. In this case, it got moved horizontally over to the right. Now, let's take a look at what it looks like in the graphing calculator on the TI-84. On the TI-84, which you now see on the screen in front of you, let's go to the y equals button so that we can convert our equation instead of r equal 2 into 3 cosine theta. If you don't want to delete the problem, you can, of course, highlight the equal sign and make it not highlighted by hitting enter. When you scroll back out then, what this will give you instead is that it will keep that equation in there but simply not graph it. Now we want to enter 3 cosine and hit the variable button. Whether or not you close the parentheses is up to you. It will still graph it correctly even if you don't. Because I want to see how it graphs, I am going to move over to the side by using the cursor key to highlight the 3 dotted lines and hit enter twice to convert it into that skeleton key shape, the -0. Now, I believe that last time I left in there a 0 to 2 pi. We didn't discuss yet what the problem is with theta step, so let's do that on this problem. We'll leave it where it is right now, which is pi divided by 60. Let's go ahead and hit graph and see what we get. Now that I have this going, you can see that I've got a graph. The graph, in fact, does look circular because I left it on zoom squared from the previous. You do have to be careful again that now that we've changed the equation, that the zoom fit window for the last equation may not work well for this one. In fact, if you hit zoom fit again, it would probably center the circle in the middle of the screen rather than having it over to the right. Let's see what happens if I now change the window value and theta step. Let's go to window and scroll down until we're on top of theta step. I'm going to enter the value of 1. Watch what happens to the circle when I change my theta step from pi divided by 60 to 1. Oh, wow, that is really not a circle. What's happening is that it's going from 0 to 2 pi, which is the numbers from 0 to about 6.28, and it's only pulling out the ones that are integer values 1 apart. So it's only calculating 0, 1, 2, 3, 4, 5, and 6. And like a 3-year-old who's playing connect the dots, it's trying to connect the dots. You've got to give it more dots. That's the problem. Let's increase the number of dots now, and let's make it, say, 0.5. Go back to Window, scroll down again to Theta Step, and let's change it to 0.5. Let's see what happens when I hit Graph this time. That should be twice as many points calculated. And you'll see that it is in fact more circular, and it is starting to look like a circle, but it is not a circle. Again, like a 3-year-old trying to play connect the dots. Why do I choose pi divided by 60? Go back to the window, scroll down until you're on Theta Step, and now enter pi divided by 60. Pi is on the cursor button, so you'll hit second, and the caret symbol, and then divided by and 60. I prefer pi divided by 60 because it gives me enough points that it's able to draw a smooth curve, but not so many points that it slows down the graphing calculator to take 5 minutes to draw one graph, or completely hang it up where I have to take the batteries out to get it to wake back up again. I find that pi divided by 60 is a good middle ground. Why the 60? I chose a denominator that was a multiple of 12. 12 is divisible by 2, 3, 4, and 6, which means the calculator will be able to use exact values for multiples of angles that are multiples of pi over 6, pi over 4, pi over 3, and pi over 2. That's why I chose 60. 48 would work as well, 72 would work, but I found that pi over 60 is probably the best middle ground. And this is what produces that more or less perfect looking circle on the graph. Let's now move on to the next example. In example 3, we are asked to identify the polar curve by transforming it from a polar equation to a rectangular equation. Our polar equation is r equals 4 cosine theta plus 4 sine theta. We could, of course, simply use the graphing calculator or Desmos to graph it, and then we'd know instantly what it was. But there is some value in learning to convert, since this is one of the ways that you often have to do it if you don't already know what it looks like. In this case, we have the equation r equals 4 cosine theta plus 4 sine theta. I've rewritten the equation several times now, so hopefully you can remember what they are. The one I want is x equals r cosine of theta, because that implies that cosine of theta must be x divided by r. I will replace the cosine of theta in this equation with x over r. What does that give me? That would give me 4 times x over r. What else could I do? Well, I could replace the 4 sine theta. For that, I will need to use the equation for y. Y is r sine theta, and this would give me that sine of theta is equal to y divided by r. When looking at that equation and plugging that into my formula, I get plus 4 times y over r. This is equal to the original r. I need to isolate the x, y and get them away from the r. The easiest way to do that is to multiply both sides of this equation by the common denominator, which is r. That will then give me r squared on the left equal to 4x plus 4y. But wait a minute, we have an equation for r squared. We know that r squared is equal to x squared plus y squared from the Pythagorean theorem. That means that I can now rewrite the equation below in this form. X squared plus y squared equals 4x plus 4y. Yes, you've guessed it. This must be another circle, but the center is certainly not at the origin, or what's known as the pole in polar coordinates. Moving the x term to the left, I would have x squared minus 4x, and moving the y term to the left, I'd have y squared minus 4y. This would then be equal to 0. To find the value of the radius, I would need to complete the square on both. Pause the video, try it yourself, then turn it back on and check your answer. How'd you do? I know, it's been a while since you've done college algebra and completing the square. I'm not going to go through and explain it since that is definitely prerequisite material, but I will leave it on the screen long enough for you to pause me so that you can look at it and make sure you can follow it. Let's take a look at something else. How do you actually graph a polar curve by hand? There are many textbooks that use what's called an R theta graph on a rectangular system before they produce the polar graph. I've never been one of those people. I find it simpler simply to make a theta R table and then to plot the points, connect them smoothly, and to watch out for the curve tracing over itself more than once. I will use symmetry to help if I can, but basically what I do is I produce a table. And yes, I do mean a table. A table means, of course, like the old XY table from, oh goodness, was that what, middle grades? Perhaps 6th, 7th grade? Yes, you need to produce a table. You need to remember, however, when you produce the table, that while theta is the independent variable and r is the dependent variable, that the ordered pairs are given in the opposite order, r theta. So whether you write theta r, as I like to do, because I know theta is the independent, or whether you want to leave it in the format of the ordered pair, doesn't really matter as long as you're consistent. What do you choose first? You better choose theta. Theta's the independent variable. Whichever form you write it in, you're going to pick the theta values. And what do you pick? Well, of course, you pick the ones you know, basically from trigonometry. These are the ones that are multiples of 0, pi over 6, pi over 4, pi over 3, and pi over 2, as well as, of course, pi. Those are the ones that you would naturally choose. Now, do I really expect you to graph these by hand? Me personally, no. However, I will tell you that there are Calculus 2 courses where students are expected to do this by hand with nothing more than a scientific calculator to help them estimate values. I, however, will let you use the graphing calculator or Desmos in order to graph it. I'm more interested in can you use this in order to compute areas or arc lengths. Let's move on and now talk about symmetry. How do we do symmetry and how can we use symmetry to help us graph? In symmetry, we're talking about the same kinds of symmetry that we talked about for a rectangular coordinate system. That is symmetry with respect to the x-axis, the y-axis, or the origin. On a polar graph, of course, this would be symmetry across the polar axis, symmetry across the line where theta equals pi over 2 down to 3 pi over 2, or symmetry with respect to the pole. It won't bother me if you continue to call it x-axis symmetry, y-axis symmetry, and origin symmetry, however. This is what we're talking about. We don't see x-axis symmetry very often in rectangular systems because we're mostly looking at functions. However, when we're dealing with polar coordinate systems, we're often not dealing with functions. We have circles, ellipses, and hyperbolas and sideways parabolas. None of those are functions, and we don't really care. We just want to know, does it have symmetry? How can you tell? There are several ways to do it. You'll see in the graph here in the picture that this does have symmetry if I fold it along what would be the x-axis if I superimposed a rectangular system on it. If I fold it on the polar axis again, it would be symmetric and touch itself, lay on top of itself, if you will. That's part B. There is another way to think about it. It is going to be symmetric across the x-axis or polar axis if replacing theta with negative theta does not change the equation. Now, what trig function do you know that will not change the equation? You're right, that's got to be cosine. The reason is when you write cosine, hang on while I get back down to where I belong, the cosine of negative theta is the same thing as the cosine of theta. This means that it is an x-axis symmetric graph. When we're looking at this does not give us any problem in folding it as far as a polar graph goes. The cosine of negative theta is the same as the cosine of theta because in the rectangular system, cosine is y-axis symmetric and theta positive would be to the right and theta negative would be to the left. However, on a polar system, remember that positive theta would be up here and negative theta would be down here. So strangely enough, on the rectangular system, what makes cosine an even symmetric graph on a polar system produces the opposite result. It's x-axis symmetric. I know, it's a little confusing. This is an example of something called a lemniscate. If you look carefully at this letter C here in the center, it has a small mark at the bottom, which means that when pronounced, that C is pronounced like an S. Perhaps one of the easiest ways of knowing that a polar curve is symmetric about the polar axis or the x-axis is by noting that if r theta is on the graph, then r negative theta is on the graph. In other words, along the same concentric circle, if the positive angle and the negative angle both give you a point on the curve, then it is probably going to be symmetric with respect to the polar axis. Let's take a look at the second kind of symmetry, which has to do with the y-axis. This symmetry, unlike the previous, does not have an axis. Remember that in the polar system, there's only one axis, which is a ray from the pole out along what would be the positive x-axis. There is no axis running vertically at all. That means that instead we have to consider this to be symmetry across the line along either theta equals pi over 2 or theta equals 3 pi over 2 or any 2 pi multiple thereof. How do we know then that this is symmetric across that line? If you replace theta with pi minus theta and it doesn't change the equation, then you definitely have a symmetric equation about the y-axis or that line. Now, what can we think about the relationship between the points on it? That means if r theta is on the graph, then r pi minus theta also has to be on the graph. What would that look like? Well, that simply says that if I'm on the same concentric circle and I have this point here on the graph, then if I take pi and I subtract this, that the point with the same reference angle must also be on the graph. And then in this case, it will lay on top of itself if you fold along the line that goes through the pole and pi over 2, or the pole and 3 pi over 2. This is another example of a lemniscate, but in this case, notice that the loop and the circular part is along a vertical, what would be the vertical axis if it were still a rectangular system. Notice that the equation has sine in it. Again, when we had cosine in the equation, that inner loop lay along the polar axis. But now that we have sine in the equation, that inner loop is laying along the line that goes through pi over 2. This is definitely a pattern, and this is the pattern. Let's take a look at the third kind of symmetry, which, as you know from rectangular systems, is symmetry about the origin, or in this case, the pole. In this case, if we replace r with negative r and it doesn't change the equation, then we must have a pole symmetric graph, or in rectangular coordinates, we would call it origin symmetric. One way to think about it is that you'll fold it twice, once on the x-axis and once on the y-axis, or once along the polar axis and once along the line of theta equal pi over 2 or 3 pi over 2. In other words, if r theta is on the graph, then negative r theta is also on the graph. These are ones where they are on the graph if they're along that 180-degree line. You can tell by looking at this equation that this equation would satisfy that condition, since replacing r with negative r and then squaring it would not change the equation at all. Let's see what the graph looks like. This graph is called a lemniscate. I know it's a crazy word, and I know that Word does not like the word and wants me to tell it that I've misspelled something, but in fact I have not. It is a lemniscate. It looks like a figure 8, so I think skate, figure 8. It works for me. You can tell that it is origin symmetric, or symmetric with respect to the pole, because if I were to fold this down along the polar axis, it would now end up here, and then if I folded it this way, it would lay directly on top of itself. Now, do you have to have symmetry to graph? No, of course not. Does it help? Yes, it helps, but it's not necessary. You can graph as long as you pick enough points. But again, I'm not expecting you to graph by hand for the most part. I'd be happy if you know how to use the technology to produce the graph you need. This will be the end of this video, which is covering how to identify different curves when converting from rectangular to polar and back. It also covered symmetry. In the next video, what we're going to do is just play. It's time to play and have fun and see what we can do with polar curves and what kind of wild figures we can draw with, yes, just a plain old decade-old graphing calculator. See you in the next video.